look today are forward stepwise, ridge, lasso, and large forms of regression. Now, if you didn't follow the previous session and do not know much about LARS, what you can check over here is we have that page available for your review over here. So over here you can find about ordinary least squares method of regression, and in case this is in continuation to the previous session. Now what happens is that this is just a brief about what regression is. When targets are real numbers, the problem is called a regression problem. Linear regression implies using a linear method to solve the regression problem. Now so now, what are penalized regression methods? Now, what happens is if you are given a data set and you don't have enough data points in it, such that the data points are lesser in comparison to the number of attributes you have. Now, in this example of finding the salaries of men with respect to height, men's salaries with respect to their height. Height is on x-axis, salary is on y-axis, and you're trying to predict y. Now, if you are what would happen if you were given only 2 points? Now, if you were given only 2 points, then what would happen? You would never get a good solution, because a line has 2 degrees of freedom, and if you only have two points, that means that number of points is equal to the number of degrees of freedom, and this would result in poor predictions, and the lines hit the points used to draw them, but there is a lot of variation among lines drawn with different pairs of points. Now, penalized linear regression provides a way to systematically reduce degrees of freedom to match the amount of data available and the complexity of the underlying phenomena. Now, if you don't have too much data and you were trying to too much data is not there, and you have to somehow work with an algorithm, then then uh, then what would happen is that if the number of points is equal to the number of degrees of freedom, then predictions are not very good. And penalized linear regression solves this problem by reducing the degrees of freedom. Now, how do I do that? How do we do that? Before we get into the depths of the different versions of regression methods, we would see how we are referring to attribute, how we are referring to the labels. Now, attributes and labels, just as we call them, they are also called attributes, are also called predictors, features, independent variables, inputs, and labels are also known as outcomes, targets, dependent variables, and responses. Now, oftentimes these are the mathematical notations of putting a matrix before you. If it's a number of rows over here is m and number of columns is n, this is an m by n matrix. This is an m by n matrix. Number of rows, number of columns, yeah. And similarly, you can figure out for this for the other matrices that this is an m, number of rows is m and number of columns is 1. This is an m by 1 matrix. 1 second, folks. Hello. Yeah. So what now? The thing is that if you want to predict if y is your target yeah, dependent variable, right? Now, if you call the prediction method on xi, you would get y, and the ways to check the performance. How do you check the performance measure of a regression problem? You check it by mean squared error or mean absolute error, and when we say we have a linear relationship between attribute and outcomes, basically what we mean is that we can write down our problem using mathematical notations such as these. Yi is roughly equals to xi multiplied by beta. Beta are our coefficients, and over here you can see it when expanded to individual constituents on the right hand side. Forward stepwise regression, what does it say now? It says that it's an algorithm, which I would explain. This is plain English well, and there shouldn't be too much problem in it. We have a column list, and now forwards, before getting into that, there's a forward stepwise regression. What does it do? It helps us figure out which attributes are most relevant to our problem of predicting y. Now, best subset selection is that you uh, create a loop, find out errors for everyone. Best subset selection is a is a naive approach to creating a subset of attributes. Forward stepwise, what it does is that this is the algorithm which we're going to use for that. Now, first it says that initialize column list to null. So we are assuming that we don't have any attributes. Then we are saying that break x and y into test and training sets. When you were breaking x and y into training sets, you were before we get into training, this is always done. This is a must. Which this you always do whenever you are solving a machine learning problem. Now, for well, if you know y and if you know x, then the problem is supervised. And at times, for unsupervised problems, you don't have y, you only have x, and you have to give some kind of prediction. Now, for number of column in x, so as many attributes as you have, what you have to do is, for each trial column, you pick a column, you build some matrix of x using column list plus trial column. So in your attribute, column list is an attribute. For that, you keep appending a trial column to your column list and train OLS. OLS is the ordinary least squares regression method that we saw over here. Refers to linear regression. Here you simply have an equation like this where we were solving the equation. I have written it down over here as well. Now, so train OLS on submatrix. Submatrix of what? Submatrix of attributes, and store the residual. RSS is residual sum of squares. The residual, basically, this is the error, RSS error. Now, when you do that, after you are done for each trial column and column not in column list, once you're done doing this, you are done with selecting your trial column. Next step is to append that column. Now, which column do we append? After we are done with all our trial columns, we are able to find out that there will be one column that minimizes RSS error the most, and we append that column to our attribute list, column list, and we also append the error that we get. Now, when we run this algorithm of forward stepwise regression, you will get a curve like this. For as you keep appending the attribute list, you would see that your error, a root mean squared error, goes down with the addition of attributes. Now, over here, how do we control the overfitting? By penalized regression coefficients. Now, when you are using penalized regression coefficients, the way to control overfitting is to ridge regression. Now, if you this equation I did not share earlier in the previous session, but it might seem complicated. What is happening is that when you look at it, this is your error term basically. This is why this is your prediction, beta naught plus xi beta. This is your prediction. This is your true value. You're subtracting it and sum of squares. So this is a square, and you are giving it a summation, and then you're giving it, multiplying it by 1 by m. So this is mean sum of squares. And argument min means that what essentially you are doing is you are finding for beta naught, for all, you will minimize which variable you're trying to minimize, beta naught and beta. Now, ridge regression changes this equation from r root mean squared, not root mean squared, it's some mean squared error, MSE to MSE plus some penalty. This is your penalty, this is the penalty, alpha times beta transpose beta. Now, when you do that, what happens with this ridge regression is, okay, one point to note over here is that ridge regression is available in scikit-learn. If you simply choose to use linear regression with scikit-learn, it will give you the OLS version of it. And now, so over here, as you see, right, minus log alpha, we are trying to plot our error, and we are trying to plot our negative log of alpha. Alpha is our penalty, is a term in our penalty coefficient. Folks, are you not able to hear me? Okay, thank you, Ati, for responding. We would get back to our lecture. Why penalized linear regression methods are so powerful? They are powerful because they are extremely fast. Model training is extremely fast, and variable importance information is also with us. We are using how variable importance information is with us, because we are using the forward stepwise. We aim to use the forward stepwise mechanism to figure out which attributes are most relevant in decreasing the error term. Reliable performance on wide variety of problems, particularly where attribute matrices are not very tall compared to the width. So if the number of attributes is too much in comparison to the number of data points you have in your training data, then you would apply, it would be beneficial if you apply penalized linear regression to that problem. And if the problem requires a linear model, then also you can apply this model. Now, equations, we look at the equations a bit. This is your Y matrix, a matrix of number of rows are n by 1 matrix, and this is your n by m matrix. So for each row in X, you would have a y variable, y value, and there are going to be as many m values as there are columns in the attribute matrix. That's because when we would multiply xi and beta, how the multiplication would happen, we would basically uh, okay, so when we would multiply xi with beta, what would happen? Matrix multiplication tells us that each row is picked from the first attribute, first variable, and multiplied with x11 will be multiplied by beta 1, x12 will be multiplied by beta 2, and so on so forth. X1m will be multiplied by beta 1, and you would get a term uh, to represent y1 for y1. And prediction of y1 is done like this: you multiply xi with beta 1, you get a matrix, and when you multiply x with beta, the matrix you would get would be m by 1, n, one second, number of columns is m by 1, you would get number of columns, number of 1 by m, 1 by m. Number of, okay, I'll recheck that. I'll skip this slide. There's some confusion over here that if we multiply x, the number of columns is m, and okay, so no, yeah, n. Okay, so number of columns is n, right? It will when we multiply x by beta, it would be of the same dimensions as y. The way to get it is that number of rows in x matrix and number of columns in beta will give you the size of your output matrix when x is multiplied with beta. Now, in the next slide, we see that this was the minimization problem for OLS. I had explained it in a bit after taking a bit time. Next comes is ridge regression, where you have where we were seeing alpha over here, but over here they have the author chose to use lambda. That is not a problem. You can change it to any Greek value that you as you like, and this is beta transpose times beta, which is essentially means that you are getting a square of each term in beta. Now Lasso regression, what Lasso regression does is equation for Manhattan disinfinity. You don't take the sum of squares for beta values. You take the mod of each value, norm 2. This is mod of each value, and add them with your coefficient, penalty coefficient. Now this is done. Now forward stepwise regression algorithm for computing beta, what happens is you want to compute beta also, right? That is the ultimate goal. We know the x, we want to compute beta. Now how do we compute beta? In forward stepwise regression, you initialize beta, and each step you find the residual errors after using variables already chosen, and determine which unused variable best explains residuals and add it to the mix. The problem over here with the forward stepwise is that we are unreservedly incorporating each new attribute. We are not mentioning how much change we would bring in beta before incorporating it. We are simply we are unreserved and we are adding beta in an unreserved manner, while in least angle regression algorithm for computing beta tells us that we are not going to be doing it in unreserved manner. We are going to modify it based on the correlation we have with the error function. So initialize all betas to 0. At each step, determine which attribute has the largest correlation with the residuals, which is, this is also a term for errors, and increment that variable's coefficient by a small amount if the correlation is positive. So if the correlation is positive, you would increase the beta, and if the correlation is negative, you would decrease the beta. So earlier we had used forward stepwise regression to for selection of attributes. Now this is forward stepwise regression algorithm for computing beta. And this is a plot that shows how the your beta values go. It's like overlapping. We had just simply drawn computation of beta values all at once, all in a single plot. And over here we see, as we take more and more steps in LARS algorithm, mean squared error goes on decreasing. All right, folks, this was all about uh, the various flavors of regression, various algorithm used in for the problem of regression, linear regression. And I'd open the floor for any questions. Do you people have any questions? Can we use Ridge for our incident reporting and searching systems? Ridge, if you are in example ServiceNow, what are you trying to predict in ServiceNow? You would have to explain it a little bit. What kind of problem is it? You were trying to, what are your attributes? What are you trying to learn in your data set? Could you elaborate a little bit? Well, Ridge is basically, I'd show you this slide again. When the targets are real numbers, the problem is called regression problem, and linear regression implies a linear method to solve a regression problem. Now, is your problem a regression problem? If your problem is a regression problem and you can apply a linear method to that problem, you would be able to use the ridge regression, otherwise not. So we keep these 2 points in mind, and this should help you. Any other questions? Any of my applications, say Java or .NET, would talk to these incident portals, get the nature of my search based on algorithm, and convert into XML nuggets. Did not understand it. I could not understand it exactly what you're trying to ask. You can unmute yourselves and talk to me if you want. I did not understand the question. You would have to unmute yourself and talk to me if you want.
Hey, hi, Ashish.
Yeah, hi.
Yeah, hi. I have a requirement like, say, for example, if my front end, say, Java
Yeah.
or .NET application, front end application,
Okay.
so any user comes and searches, say, for example, I need a VDI or I need the list of reports which is about the tickets which say about the VDI, how what sort of VDI requests have come. So this application in turn must talk to my service now or any other portal, say for example Azure or Jira or anywhere it must talk. I mean, and it must return the nature of the exact nature of that query which I have fired.
So you mean to say that there is service now with the incident raised incidents, and you want to predict which, you want to find out which one are relevant to VDI. Let's say
Yes,
you
yes,
want to
and
return.
it must predict it. It
Yeah,
must
it
predict
must
exactly.
predict if an incident raised in for service now is related to VDI or not.
Correct, correct, yes, correct.
So this is a problem of classification, not regression, because in regression you have real numbers. If you want to use regression method, let's say I show you how you can use regression algorithm for classification. The book which I was reading for preparing this course material showed how you can use regression, ridge regression for the purpose of classification. We never do it in practice, but theoretically it is possible. I repeat again, theoretically you can do it, but in practice you would have to use classification. Do you copy? Did you hear me? Could you acknowledge yes in yes or no? So you would not
Yes, yes.
use ridge regression for your problem, but you can use this algorithm. So what you would need to know is one hot encoding. So one hot encoding, what it does is, so VDI is like yes or no, right? Values for VDI, values for
Yes.
VDI column, yes or no. Now, if you have a yes, you would say VDI yes and VDI no. Now, if the input is yes, let's say, you would say 1, and otherwise you would say 0. Otherwise you would say 0, and if it is no, then you would say 0 and you would say 1. Now you this is your what do you say? This over here is how you would convert your labels from alphabets to numbers, and then you would try to predict if VDIS is. Now when you would do the prediction for VDIS, it would be some value between 0 and 1. Now you can set a threshold that if my VDIS value is greater than 0.5, I would I would assume it is a yes and predict that the incoming ticket in ServiceNow is about VDI. Got it? But never do it. I'd write it over here also in caps. Do not use regression algorithms for classification problem. Okay.
Okay.
Any other questions? I request people go on mute, or we would have to close the session because we are running out of time. Any other questions?
Would this slide be shared?
Yeah, I would prepare a web page like this one, right? You were not there in the previous session, so you can go through this. I'd share the link again with you in the chat, and you can learn a few things about linear regression from it. And this is in continuation to that only. And you would always have look at it whenever you with if you have access to a device and internet connection.
Yeah, sure. Why not?
Yeah. Allow me some time. I would do it by end of day or maybe tomorrow.
Yeah, sure. And can we talk to you for our problems? Like if you
Yeah,
need
yeah.
any assistance?
Anytime. So any other questions, folks? If not, then we can close the session.
Nothing for my end, Ashish. Nice session. Thank you.
Okay. Thank you, folks. Thank you. We'll close the session now.
Thank you. Bye-bye.
Bye.